So welcome you to this problem solving session. So what we'll do in this session is we'll try to solve some of the problems from assignment number 4. So let us first pick up problem number 1. So problem number 1 from assignment number 4. So what you are given is x1, x2, xn are IID, binomial 1 theta. Your theta is unknown parameter, which is belongs to the open interval 0 to 1. What you are interested in estimation of theta under the loss function L theta A, which is squared error, right? So A minus theta whole square. So in this case, certainly your xn space would be 0, 1 only, because you are interested in estimating theta, which belongs to 0 to 1, and theta belongs to capital theta. That is given to you. So what it says is you consider a randomized decision rule. So this is a randomized decision rule. Randomized decision rule means it does a randomization immediately after observing the data before arriving at final decision. So what is a randomization? It says probability of taking xn A when x is observed. So if A is x bar, the probability of taking xn x bar is n upon n plus 1. And with remaining probability, that is 1 upon n plus 1, A is equal to half. So what this decision rule says is after you have observed x, your xn is x bar with probability n upon n plus 1, and your estimator is half with probability 1 upon n plus 1. So immediately after taking the observations, you are not deciding what your xn should be. So what it says is after you have observed x, you go for a randomization, which could be tossing a coin, because there are only two outcomes, with probability of head as n upon n plus 1 and probability of tail as 1 upon n plus 1. So after you have observed x, toss a coin. If head turns up, you estimate theta by x bar. If tail turns up, whose probability is 1 upon n plus 1, you estimate it by half. It says compare the supremum risk of this estimator with the supremum risk of x bar, and so that supremum risk of this estimator is smaller than the supremum risk of x bar, which in fact would prove that x bar is not minimax. Right? So first let us try to see what is r theta x bar. X bar is a non-randomized decision rule, so this is same as expected value of x bar minus theta whole square. In the binomial case, you know that x bar is an unbiased estimator of theta. So expected value of x bar minus theta whole square is nothing but variance of x bar. And variance of x bar is nothing but sigma square by n. Sigma square is the variance of single observation, which is theta into 1 minus theta divided by. So r theta x bar turns out to be this. So what is the supremum over theta belonging to capital theta of r theta x bar? So what is the supremum of theta into 1 minus theta when theta is between 0 to 1? So you can see theta into 1 minus theta is theta minus theta square. So derivative is 1 minus 2 theta. That is positive if theta is less than half. So that means it is increasing if theta less than half and decreasing for theta greater than half. So this is r theta x bar. So that means supremum would be attained at theta is equal to half, which is nothing but 1 upon 4n. Now what I'll do is I'll find out the supremum risk of this randomized estimator. Now note that here, before taking expected value of x bar minus theta, there is a randomization involved. So I look at first randomization, so which is L star theta delta x. So that means after observing x, the randomization. So what is this? After observing x, so which is expected value with respect to delta of a minus theta, which is yx minus theta whole square, right? So the random variable, corresponding random variable, and denoted by yx. What is yx? Yx is x bar with probability n upon n plus 1, so this is same as x bar minus theta whole square into n upon n plus 1, plus yx is half with probability 1 upon n plus 1. So half minus theta whole square into 1 upon n plus 1. So this is L star theta. So I can now talk about r theta delta, which is expected value of L star theta delta. Now x is the random. This is the second stage randomization. Second stage randomization is with respect to the data. And what is that? That is nothing but n upon n plus 1 into expected value of x bar minus theta whole square plus 1 upon n plus 1 into expected value of half minus theta whole square is same as half minus theta whole square. All right, so how much this turns out to be? This is sigma square by n, so n theta into 1 minus theta divided by n plus 1, because this would be theta into 1 minus theta by n, so n gets cancelled, so this. And this would be nothing but 1 upon n plus 1 into half minus theta whole square. You can check this expression. This expression turns out to be how much? 1 upon n plus 1 you can take common. 1 upon n plus 1, it becomes theta minus theta square plus 1 by 4 minus theta plus theta square, which is 1 upon 4 times n plus 1. So risk in fact does not depend on theta. So what is the supremum of theta belonging to theta of r theta delta? This is nothing but 1 upon 4 n plus 1, which is certainly less than 1 upon 4n, which is nothing but the supremum risk of x bar. So that means in terms of a supremum risk, delta estimator performs better than the x bar. So x bar is not minimax for estimating binomial probability under the squared error loss function. You can prove it by many other ways. In fact, you can find out what exactly the minimax estimator would be. Minimax estimator under the squared error loss function is nothing but the posterior mean. Now, posterior mean depends on what your prior distribution is. So yeah, so you can prove this minimaxity through other arguments, which I have explained in one of those assignment problems later on. Now let's do the problem number 2. So what are the conjugate priors? That is what he's asking for. So that means what should be the prior so that the posterior distribution again belongs to the family of a prior distribution. So A is nk theta ik. That means x1, x2, xk are IID normal theta ik. Certainly in this case we can see conjugate prior would be nothing but normal with certain mean mu and certain covariance matrix sigma. For theta, that could be a prior distribution. What should be binomial in theta? That means your data is coming from binomial. Binomial is theta to the power x 1 minus theta to the power n minus x. Now you want posterior distribution to be again of that type. So now theta into 1 minus theta is coming, so it looks like I should take posterior prior distribution to be beta, and then posterior becomes again beta. So this is beta, alpha, beta. Okay, what is a uniform 0 theta? Uniform 0 theta, that means it turns out to be theta to power n. So what should be your prior distribution of theta so that you get again in the form of prior distribution? Now 1 upon theta to power n is coming. So what should I choose my prior distribution to be for theta greater than 0? So it should be a power kind of a distribution. You can check that. Now, in the case of last E, binomial n theta. What should be the binomial n theta? That means n is a parameter here. Here theta is a parameter, so that is by beta. Here n is a parameter. So what is this? Factorial n, factorial x, factorial n minus x, theta to power x, 1 minus theta to power n minus x. So 1 minus theta to power n would come. And factorial n, factorial x, factorial n minus x would come. So it looks like I can take n to be Poisson. So Fsn is e to power minus lambda, lambda to power n by factorial n. You can truncate it if you want, because n here is a positive integer, so you can truncate it so that n is equal to 1, 2, so on. And you can put here some constant. Now this could be what was the d part? D is exponential. So exponential could be inverted gamma. So you can complete this, right? Now let me do problems one by one. Now the third problem says x1, x2, xn are IID Poisson theta. Theta belongs to 0 to infinity, is unknown. Under the square error loss function, so your loss function is this. What is my claim? X bar cannot be base with respect to any proper prior. So let us recall the result which said that if you have any unbiased emitter, then if it is base under square error loss function, so the base risk should be 0. Is x bar as unbiased in this case? Because Poisson mean is theta, so expected value of x bar is theta. So if it is base, its base risk has to be 0. So let us try to see what is the base risk of this estimator. So first I consider the classical risk r theta x bar, which is expected value of x bar minus theta whole square. Theta x bar is unbiased for theta, so it is same as variance of x bar, which is same as sigma square by n. And what is the variance of Poisson? Is same as the mean. So it is same as theta by n. Right? Because variance of Poisson is same as its mean. So what is r pi x bar with respect to any estimator? That is same as expected value of theta by n. Or expected value of s by n, right? Now this is 0 only if probability of s is equal to 0 is 1, right? then only expected value of S is 0. But this is not a proper prior, because my theta is positive. So what does this suggest? This suggests that base disk of an unbiased emitter cannot be 0. So X bar cannot be base by the result which we did. All right. So, okay, let us do problem number 4 also. So X is a random variable with PDF f theta. Theta belongs to capital theta. Is a parameter space. Pi be a prior distribution. For a real valued function g theta, so g theta is the estimate. And w theta is a weight, so what you are assuming is integral over theta, w theta, g theta, d pi theta is finite. So I consider estimation of g theta under the loss function L theta a is w theta into a minus theta whole square. So it is a more general loss function than the squared error loss function, because if you consider w theta to be 1, it reduces to squared error loss function. So it says under this base estimator delta pi x, which is integral over theta, w theta, g theta, f theta x, d pi theta, divided by integral over theta, w theta, f theta x, d pi theta. So that is what it says. Now, before I do that, note that if w theta is 1, then it is f theta x d pi theta. So it is a conditional distribution of x given theta, and then you integrate out this density of theta. So it is a basically what happens with this, you get marginal of x. What is this? W theta comes outside because w theta is 1 if, then g theta f theta x d pi theta by marginal of x. So that means integral over of g theta with respect to the posterior distribution. So in that case, if w theta is 1, this becomes posterior mean of g theta, which matches with our observation that if you have a squared error loss function, the base estimator is the posterior mean. If it is a loss function of this type, it is a kind of weighted posterior mean with weights coming from w theta. The idea of the proof is exactly the same as we did in the case of squared error loss function. So let's consider L star theta delta x. That is nothing but expected value of w theta, and randomization is in terms of random vector yx minus theta whole square. What is r theta delta? So this is for expected value y for a given x. So this is same as expected value of x, expected value of y of what is r pi delta? This is expected value of s, expected value of x, expected value of y and x of w theta yx minus s whole square. Is that okay? So as we did in the case of square root loss function, we need to just interchange certain integrals. So what I do is, now when I do this, this is not Ex, each is with respect to distribution of E of x given S. So this is with respect to joint distribution of x and s. This can be written as E of x, E of yx, and E of s given x, right? Basically this E of x and E of s given x is nothing but these two expectations. And I take E of x, which is just marginal distribution of x, totally outside. All right, because this is with respect to joint distribution of s and x. The first outer two expectations, if you combine, they are with respect to joint distribution of x and s. But joint distribution of x and s can be written as conditional distribution of s given x into marginal of x. So this is a marginal of x. So if you want, I can add one more step. I write down this expectation as E of x, E of s given x, E of yx, w theta into yx minus s whole square. Right? X is outside, so x is anywhere fixed over here. So this is same as E of x, E of s given x. Sorry, E of x, E of yx, E of s given x of w theta yx minus s whole square. So what I try to do is, I try to minimize this for a given x, and I try to see which a minimizes this. So let a star, which is basically depending on x, be such that this quantity for a star is minimum. So that means E expected value of s given x of w theta. Actually, this w theta everywhere should be ws, because theta as a random variable is denoted by s. Yeah, so here it is okay. Here it should be ws, ws. So this is same as ws into a star minus, actually you are estimating not theta, you are estimating g of theta. So it should be everywhere g of theta, right? So it would be g of s, because you are estimating g of theta, not g of s. So g of s minus g of s whole square is same as infimum over a belonging to a, expected value of s given x ws a minus gs whole square. So what does that mean? That means this quantity yx, with yx over here, this is minimized at a star x. So that means this quantity would always be greater than or equal to Ex E of yx E of s given x of ws, and then a star minus gs whole square. So the only thing is, if I can prove there is no yx over here, so this becomes E of x E of s given x of ws, because though there is no randomization with respect to yx, because a has become a star, which only depends on x. But what is this? This can be written as E of, this is again with respect to joint distribution of S and X. Joint distribution of S and X can be written as conditional distribution of X and S and marginal of S. So, marginal of S, conditional distribution of X given S, W of S into A star minus G of S. So, what you need to show? If this A star was same as delta pi x, then I was done. Then it would have been a risk of delta pi, and this estimator would have been the base. So, to show that delta pi is base, you just try to show that A star is same as this estimator. That means the minimizing. So, I just need to show A star is same as this. So, what is the A star? A star is something which minimizes this. So, E of S given X. So, let me call this as psi of A, E of S given X, Ws to A minus Gs whole square. So, I need to minimize this quantity. So, what is this? It becomes A square expected value of S given X into Ws minus twice A expected value of S given X of Ws into Gs plus E of S given X of Ws into G square S. I need to minimize this. W is a positive function, so this quantity is going to be positive. So, I see its behavior. So, psi prime A is twice A E of S given X W of S minus twice times E of S given X Ws Gs. So, it is increasing if A is greater than this divided by this. So, that means it is increasing after A something, before that it is decreasing. So, it is like going to be like this. So, minimum would be where this quantity is 0. So, A star, which is tending by A star x, turns out to be, this is 0 if A is same as this divided by this. So, this is E of S given X of Ws Gs W of S. But what is this expectation? This expectation is respect to conditional distribution of S given X. But conditional is always proportional to the marginal, joint. So, I can write down the joint divided by the marginal of X. Here also I integrate with respect to joint of S and X divided by the marginal of X. But marginal of X and numerator and denominator both get cancelled because X is a fixed quantity. So, it is as if I am integrating both numerator and denominator with respect to joint distribution of X and S. So, which is nothing but integral over theta, because S is a variable, W theta G theta into joint density of S and X, which is same as conditional distribution of X given S equal to theta, which is F theta X, conditional distribution of X given S, then the distribution of S, which is the prior distribution, so which is d pi theta. Denominator exactly the same way, integral over theta, W theta. Then the integral with respect to joint distribution of X and S, which is same as conditional distribution of X given S, which is F theta X. And then the prior distribution, which is d pi theta. Marginal of S, which is prior distribution, which is same as d pi theta. And that is what you needed to prove. So, let me take a break over here. In the next module, we'll try to do some more problems. So, that's all for this problem solving session. We'll try to solve some more problems of assignment 4 in the next problem solving session. Thank you.